Today our discussion topic is thermodynamics. See, in the branch of thermodynamics, how the heat can be transferred from the system to the surroundings. So here we are going to discuss the systems first. There are the three systems. One is open system, closed system and isolated system. See here, if you observe this open system, closed system and isolated system. If you observe this one, if it is a cylinder, it's a gas present. If the system is open, definitely what happens that the gas can be emptied out, some other material, other matter can be entered to this. So here what happens that the system, matter as well as energy both can transfer with the surroundings. What do you mean by closed system here? Only energy can transfer. What about that isolated system here? Neither energy nor matter can transfer with the surroundings. If you observe this, how can we construct this particular closed system and isolated system? If it is a cylinder, if it is made of completely isothermal things, then what happens that this energy only can transfer with this matter, it will be. Suppose if you are taken as adiabatic walls, in this case what happens that neither energy nor matter. In the branch of thermodynamics, how the system can transfer both energy and matter with the surroundings, we are going to discuss. In the laws of thermodynamics, first I am going to discuss about that first law of thermodynamics. This is a system, let the gas is present here. If you are supplied to the system to the dq here, this dq can be transferred to the gas, that can be in terms of change in internal energy and external work done. This first law of thermodynamics is a application of conservation of energy. What we are giving to the system is dq, what the system gives that changes du and dw. If I am writing this, dq is equal du plus dw. By applications of first law of thermodynamics, we have some assumptions. One is, first one, heat is supplied to the system. Next one is, heat is ejected from the system or taken from the system. In this case, see here dq is supplied to the gas. In this case what happens that dq is taken from the gas. Whenever you are giving the system to the dq is equal positive here, whenever heat is taken from the system, dq is negative. Generally we are using these applications in solving the problems. Come to the work done here, work done assumptions. If you are supplied to the system, the gas work done, the work done by the gas is equal dw is positive, work done on the gas dw is negative. This is about that assumptions of dq and dw here. Both dq and dw, they depends upon the path. What about the du here? It only depends initial and final position. So du we can write down ef minus ui. It only depends upon that initial internal energy and final internal energy. Whereas dq and dw, what happens that it depends upon the path. Next, the work done, how can we determine this? The work done, W is equal, if it is a variation of P into dV here. So there are so many processes in solving the questions we come across. One is isobaric process, isochoric process, Next, adiabatic process, isothermal process. There are the different process, depends upon their conditions what are given. We will discuss now how the work done is changes from process to process. We are going to discuss. First, isobaric process. Now, we are going to discuss how the work done is changes in different process. How can you take this isobaric process? In this process, pressure is constant. Then, W is equal to integral P dV here, V1 to V2. So, pressure is constant, we taken outside, integral dV V1 to V2, this can be equal to P into V2 minus V1. So, directly suppose if the process is an isobaric process, here we are using work done by the system V is equal W is equal P into V2 minus V1. Next one, isochoric process. What do you mean by isochoric process here? Initial volume is V here. During this process, this initial volume doesn't change. So, hence definitely if the change in volume is 0, if you observe this, work done in isochoric process is 0. After that, isothermal process. Here, they are taken as temperature is constant. Last class we discussed the internal energy is a function of temperature. If the temperature is constant, internal energy is a constant. Therefore, in this process, du is equal 0. If the temperature is constant, we know this PV is equal constant. Here, how can you find out this work done in this process here? PV for the ideal gas, we know this PV is equal to nRT. So, P is equal to nRT by V. So, we are taking this equation and substitute in our general equation integral P dV to V1 to V2. So, this can be what is that nRT by V into dV V1 to V2. So, this can be nRT ln V2 by V1. This is work done in isothermal process. Here next one, adiabatic process. So, this is another process, adiabatic process. So, here our assumption that if the system is a gas, here whatever is supplied to the system, this dq has to be 0. Then dq is equal to 0, we are taking this adiabatic process Pv to the power of gamma is equal to constant. So, this can be taken as k here, P is equal to k by V to the power of gamma. So, work done is equal, what is that? P dV V1 to V2. So, every process, if you take that adiabatic process, isothermal process or isochoric process, we are starting from the same equation. We are substituting the same value of the pressure k by V to the power of gamma into dV V1 to V2. So, this can be what is that k into V to the power of minus gamma dV V1 to V2. So, this can be what is that V to the power of minus gamma plus 1 by minus gamma plus 1 V1 to V2. So, work done is equal to k by 1 minus gamma into V2 minus V minus gamma by V1 1 minus gamma here. Next, if you have taken this k inside, so k is equal Pv to the power of gamma is equal constant. Hence, we can write down k is equal P1 V1 to the power of gamma, P2 V2 to the power of gamma. This is the pressure at one position, and at the same time the volume of the gas. Here this is the second time, the second case, the pressure and volume. We are substituting the same values of this one. So, P2 V2 to the power of gamma instead of k into V2 to the power of 1 minus gamma minus P1 V1 to the power of gamma, P1 to the power of gamma here. So finally what we got this, W is equal to 1 minus gamma into P2 gamma plus 1 minus gamma here, gamma cancel, minus P1 V1. So we can write down from the ideal gas equation PV is equal to nRT. So we can write down nRT2 minus nRT1. So nR by 1 minus gamma here, T2 minus T1. This is work done in adiabatic process. In solving the questions, we are applying this work done in different process. Next, come to the next topic here, how we are applications this particular work done in different process. So dq is equal to du plus dw here. So in the process, first one we are going to discuss about that cyclic process. What do you mean by cyclic process? You take any parameter like pressure and volume, or you can take internal energy and volume, or you can take volume and T. You represent the gas process by taking any of the two parameters, and total process can be explained by the graphically. That process what we are calling as indicator diagram. Here suppose if the process it starts from point A, it goes to some point B and again comes to point A, then process what we are calling as cyclic process. So round trip. See here, suppose this is the process here, A, B and next to C here, next to D here, it goes this one. Here it starts from A, it goes to B, next comes to C, next comes to D, again reaches this point here. So here what happens that it starts from the point A and again during so many process, finally it reaches the initial point. So this process what we are calling as cyclic process. The diagram which explains the gas process by taking any of the two parameters, the pressure volume or volume temperature or internal energy volume, the diagram what we are calling as indicator diagram. See, suppose some process we are taking this like this, like it starts from A and B. It doesn't goes to initial point. So this process what we are calling as non-cyclic process. In the cyclic process, first what we observe is initial and final position. See, if you are taking this du, it only depends upon this initial and final position, whereas dq and dw both depends upon the path. Here initial and final positions are same, then by the definition of du what we are taking that uf minus ui. So initial and final internal energies are same, therefore in the cyclic process we can say that du has to be 0. Now we are going to discuss some problems based on cyclic process. If you observe this diagram here, this is the indicator diagram that can be observed in the monitor, that pressure and volume here. The graph is drawn. See here, there are the three processes. So one arrow A, C, B, this is the one process. It starts from A and reaches to C and again from to the B point. Next process 2, A, D and B. So two arrows can be represented by the second process. And next one other process AB, it is represented by 3 arrows. So here if you observe this, 3 paths through the which a gas can be taken from state A to state B, calculate the work done by the gas in each of the 3 processes. Here if you observe this, each process it starts from the A and each process it ends at B. Here we are going to discuss about the work done in all of the 3 processes. First we are taking the first process that is represented by the only one arrow, that is AC and B. If you observe that AC, now volume V is a constant. If you observe this, they are maintained as a, during the AC process, it's maintained as a 10 cc, 10 centimeter cube. And again C to B, it's here what happens that pressure is a constant. Here the pressure is maintained as a 30 kilopascal. So now we discussed about the work done during the isochoric process, here in our diagram, AC is our isochoric process, dV has to be 0, whereas BC is a isobaric process. This is the first process that I explained now. This BC that can be taken as this isobaric process. Now I am taking that BC process. This isobaric process work done will be taken as P into V2 minus V1.